Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. In this podcast, we'll discuss higher order iteration, and we'll do an error analysis for that. And we'll also discuss some of the issues that arise when doing fixed point iteration. In an earlier podcast, we discussed error analysis for Newton's method. Here we'll do a more general error analysis for one-point fixed point methods. We consider methods of the form x sub n plus 1 equals g of xn, and we expand g of x around x star. That is the fixed point. So we get g of x sub n is g of x star plus g prime of x star times xn minus x star, and we go on. This is the Taylor series. We take through xn minus x star to the q power, and then we write the remainder term, which depends on the q plus first derivative of g at a point between xn, the nth iterate, and the fixed point x star. Okay, that's the same equation at the top of this page. And to do our analysis, we note that at the fixed point, x star is g of x star, and we'll plug in for that on the right. The g of x star will become x star. And the iteration scheme itself is x sub n plus 1 is g of xn, and so we'll plug that in on the left. So the g of xn here becomes xn plus 1. We'll subtract x star from both sides, so we get xn plus 1 minus x star. On the right, we get x star minus x star, and the rest on the right stays the same. On the left, we note that x star minus x sub n plus 1, that's the error of the n plus first iterate. So the left side is minus the error at the n plus first iterate. And on the right-hand side, we can write all the xn minus x stars as the error of the nth iterate. Okay, and that's with a minus sign, so we're going to get some alternating signs. And we can plug all of that in. Okay, that equation is the same. The equation on the top of this page is the same as the equation on the bottom of the previous page. So the situation where we had g prime at the fixed point being non-zero, but less than 1 in absolute value in order to give us convergence, that's the case where q is 0. That you get the error at the n plus first term is related to the first derivative of g times the error to the first power at the previous term. So the new error is like g prime times the old error, and that's linear convergence. If q is 1, then what we have is g prime at x star is 0, and we have g double prime at x star is not 0. So if q is 1, we plug that in over here, and we have that the new error is related to the second derivative of g times the previous error to the 1 plus 1, or the previous error squared, and convergence is quadratic. If you had g prime and g double prime at the fixed point are both 0, but g triple prime is not 0, then q is 2, and we have that the error at the new term is related to the third derivative of the function of g times the error at the previous term to the third power, and convergence is cubic. Let's do an example. Suppose we consider the iteration scheme xn plus 1 is 1/3 xn minus 2 quantity cubed plus 2. And that as a fixed point, x star is equal to 2. It has two other fixed points which you can try to figure out, but one of the fixed points is x star is 2. If we plug that in, we get 2 minus 2, which is 0 cubed plus 2. So clearly x star equal 2 is a fixed point. G of x is 1/3 x minus 2 quantity cubed plus 2. G of 2 is 2, as we notice, that's the fixed point. G prime of x, the 3's cancel, you get x minus 2 squared. G prime at our fixed point, G prime at 2 is 0. G double prime is 2 times x minus 2, so G double prime at x equal 2 is 0. And G triple prime is just 2, so G triple prime at 2 or anywhere happens to be 2. We can plug that all in to the formula up here. The G prime at x star term is 0, the g double prime at x star term is 0, and q is equal to 2. We get minus 1 cubed over 2 plus 1 factorial, the third derivative of g, somewhere near the root, times the previous error to the 2 plus 1, to the third power. So we have the new error is 1/3 of the old error cubed. And I encourage you to say start with x0 equal 3 and see what happens to the iterates and compare with this result for the convergence analysis. As another example, we can go back and consider Newton's method and just make sure to confirm the results there. Newton's method is xn plus 1 equals xn minus f of xn over f prime of xn. So g is equal to x minus f of x over f prime of x. We take g prime of x is 1 minus this messy piece. We notice we get f prime squared over f prime squared. So you get 1 minus 1. Then you get minus minus gives you a plus. And you just get this quantity. But we note that g prime at x star gives us f at x star times other things. F of x star, that's the root of the equation that we were trying to solve. So this piece becomes 0. So therefore g prime at x star is 0. But g double prime at x star typically is not going to be 0. And so what we have is the new error is equal to this quantity, f double prime over f prime near the root, times the previous error squared. So convergence of Newton's method is quadratic. Let's discuss some of the problems that may arise when we're doing root finding. Well, if a function has multiple roots, what that means is if f of alpha is equal to f prime of alpha is equal to f double prime, etc., and the m minus first derivative at alpha is also 0, but the mth derivative is not, then we say that f has a root of multiplicity m at alpha. As an example, you can note that if f of x is 1 minus cosine x, and you consider that at x equals 0, that's a root, you get 1 minus 1 is 0. That if you take the derivative, you get sine of 0 is 0. And so what you have is a root of multiplicity 2, because the second derivative is cosine of 0, which is 1. So the second derivative is non-zero, but the first derivative is 0, so the root is of multiplicity 2. Well, when there's a multiple root, then what happens is the function is very flat at that root. So, for example, if you had f of x is x to the fifth, and you could consider x equal 0.01, well, f of 0.01 is 1 to the minus 10th, 1 times 10 to the minus 10th. That's a really tiny number, so you might think you're really close to the root in terms of x, but only the y value is so close to 0, the x value is not really so great. So what happens is that some of the iteration schemes may slow down. And let's discuss for Newton's method in particular. Suppose we take a simple equation. F of x is some constant times x minus a to the mth power. Then g of x is x minus f over f prime. I'm using some shorthand here. G prime of x is f double prime over f prime squared, as we saw on the previous page. And if we consider f of x equals c times x minus alpha to the m, and we plug that in over here and we go through the algebra and do the cancellation, it's really not very hard, we get that g prime of x is no longer 0. It's m minus 1 over m. So if m is 1, in other words, if it's a root of multiplicity 1, the normal case, yeah, so then g prime is equal to 0 at the fixed point, and we get second order convergence. But if we have a multiple root at alpha, right, if m is 2, sorry, we have a misprint here. If m is 2, then what we get is 2 minus 1 over 2 is a half, and you get g prime is a half, which is just like the bisection method, that the new error is going to be about half of the old error. If m is equal to 3, if you have a root of multiplicity 3, not 2, that's another typo. If m is 3, you get 3 minus 1 is 2 over 3, and you get 2/3, meaning that the new error is 2/3 of the previous error. It means that Newton's method is not even as good as the bisection method when m is 3. So if you have a multiple root, Newton's method really slows down, especially if it's a high multiple. So in this case, just to note that this m equal 1 is correct. This other m equal 1 should be m equal 2. and this third one should be m equal 3. How do we get around it? Well, if we considered f of x over f prime of x, well, then f of x might have a root of multiplicity m, f prime would have a root of multiplicity m minus 1. You divide them, and then you get just a root of multiplicity 1. But then Newton's method on this function is messier. One can also consider taking the m plus m minus first derivative. Disregard this f of x on the bottom. You could take the m minus first derivative of f of x and use Newton's method on that, and you'd have a function with multiplicity 1. Let's just consider another case where there's a problem, and that has to do with the stability of roots. Some problems are just inherently sensitive, and for example, if we consider the 7th power polynomial x minus 1 times x minus 2 times x minus 7, which is x to the 7th minus 28 x to the 6th plus and we change the second coefficient by a factor of about 1 in 10,000. Just change it to 28.002. What happens to the roots? Well, the roots of the original function f were just 1, 2, 3, 4, 5, 6, 7. The roots of g, well, one root is very close to 1, one is close to 2, the next one's sort of close to 3, the next one's a little less close to 4. Roots 5 and 6, well, they even have an imaginary component in them, and 7 changes quite a bit. So a small change in just one of the parameters, one of the coefficients, really messed up our problem. You can get a sense of how sensitive your solution is to the parameters by varying the parameters a little bit and solving and see, does your answer change a lot? And if it does, then you really have to worry about, is there round off error, and are there other errors in your parameters that may lead to an erroneous error. Similar issues arise if you find one root and it has a small error in it, and then you divide by that root in order to then go and get the next root, and these errors can build up. Finally, we'll have a moment of culture. Once upon a time, some students were discussing some of the professors at the university, and a senior was discussing with a freshman things that the freshman should know about the professor. And the senior said, here, if Professor A says something is obvious, it means that if you go home and think about it for the rest of the afternoon, you'll probably see that it's true. On the other hand, if Professor L says that something is obvious, it means that if you go off and spend the rest of your life considering it, the day might eventually come when you see that it's true. If Professor W says something is obvious, it probably means the class has known it was true for the last 2 weeks. And finally, if Professor F says that something is obvious, it means that the assertion is probably false. I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.